Yeah, since we're already a minute late, let's get started. It's a great pleasure to introduce Sultan Hassan, who is now Hubble Fellow at NYU and Kaggle X Fellow at Google. Sultan did his bachelor in Sudan, then he moved to South Africa, where he did his master's, PhD, and first postdoc, right, in South Africa, very different university. Then moved to New Mexico, close right across the border. So we brought him back to the Southwest since New Mexico time, and then he moved to New York, where he was a Flatiron Research Fellow at CCA, and we were sharing an office, and then he moved to the Hubble Fellowship at NYU. And Sultan is really an expert in cosmology, realization, and using machine learning techniques to study those kind of problems, and he will tell us more about that.
Thank you very much for the invite. It's been really nice to be in the desert once again. So I want to share with you some of the things that I have been thinking about, especially in the star formation and in the direction of JWST. So maybe let's get started. So I usually like to think about whatever things like new things we find is basically driven by technology, right? For instance, we know like during the Cold War, right, the development of radars, that's actually helped establish the field of radio astronomy. And this is a great book which discusses these things, like you can think about any new discoveries we have in the field or any new puzzles we get is basically by the advancement of the discovery and the instrumentation and technology. And this is lead us actually to what we see with JWST, right? So JWST is a very interesting experiment. It tried to push us into different regime, right? I like this plot because it shows, right, you have the faint on top, the faint bottom, right, upright, this is the magnitude proxy for luminosity. And then you have, this is the redshift, this is one of the nice summaries, right? And all the gray dots is from HST, right? So HST with the older technologies, we were in the very late universe. With JWST now we are able to probe any of these different sources. We are pushing the limit towards this, right? And this is the challenge. So it's very exciting now. We know many candidates in the early universe, right? Even what they call it cosmic dawn, the earliest population of galaxies. But this is pushing us towards a regime that we don't know much about, okay? So that's the interesting thing. What is the painful part is that most of our models struggle to reproduce this. So this is what you see here. This is the luminosity functions, number count of like the abundance of galaxies, right, as a function of redshift. So you have here redshift of 10, redshift of 13. This is one of the earliest results we have. Maybe they are more updated ones. And again, right, so with JWST now, and these are different models, they have different assumptions, right? But if you look at most of the models, they fail to reproduce these bright objects. So what's happening is that JWST is really pushing us towards detecting very, very massive candidates that we never thought they would exist at these times. And we all fail. So this is a failure, right? It's an interesting failure in the model side. But they all require too efficient star formation, right? So if you have a model that is bringing you a too efficient star formation, then hopefully you can naturally recover this, okay? So this is good. So whenever we have this tension between, we like tension, at the theoretician, observers too, I think. Whenever you have a tension between the theory and the observation, right? It's a place where people think maybe we can find a new physics or we can do something, and there is a big debate, always the same. I remember the same debate we had in the same times, like I think 2018, when we had the detection of the 21 centimeter global signal by edges, and it was very too deep, and it was very lively debate. We have the same debate now here. And in a statistical sense, you can think about it as there is a distribution shift, right? So what we simulate is not the real universe. What we model is not the real universe. We have some assumptions about how stars is formed, like we make so many assumptions for many things. And the observation with the systematics and everything they always have a very different distribution to what we simulate. And we need to find ways to minimize this, right? So it could be this distribution shift is a place where you can have a new physics, and there are different sources to this debate, right? So it could be in accurate measurements, right? So you can say, oh, my theory is beautiful. I don't think there is a tension here. I blame the observers and that's it. Or maybe you can say, well, oh, let's take the observation, like believe that they have done a very good job, but then we are actually lacking important astrophysics and cosmological effects. We're lacking that, and that's for true that most of the models we have, they don't have the complete picture. And maybe also even once you have a pure theoretical signal, you have to have some processing pipeline to make it like mock observation, right? So you need to add noise and dust, and you need to account for all the observation. And this is really, they all degenerate because they all could give you the same thing, right? Like you could say the observation is wrong, and then you move your distribution to some side, and then you can change the cosmology, and you can boost the Halo mass function, and you don't need too efficient star formation at that time, and then you come up with the same place. So it's very degenerate, and it's very important we address these issues as we're going forward. So if you go to archive and write JWST tension, okay, there is already now 102 papers. It's very hard to review all of them about this, and it's a very interesting debate. And I will try to highlight some of them that might just try to shed the light on what I'm trying to say. So let's go for a few examples. One of the earliest examples is by Boyle and Colchin, 2022, where basically stressing lambda CDM. He's trying to point out maybe some lambda CDM is not complete. And the fact that if you assume that, which is perfectly a basic assumption to take, is that stars forms from the baryonic reservoir of halos. So if you have the rho b, which is the density of the baryons in your halos or in your environment, and then you form stars from there, right? What they find is that when he takes the JWST observation, so the masses that he gets from JWST observation, they realize that they are a lot more higher and larger than what the available baryonic reservoir is. So you basically, you can never, like the masses that is estimated from the observation, they are a lot more massive than what you expect from any rho b or the density of the reservoirs in halos. So that's a clear tension that lambda CDM might not be an accurate model to reproduce this JWST observation. So here he blames cosmology, okay? Let's go to the other one. This is another interesting paper came recently, which is tells you, okay, so if you have too efficient star formation and you have all these sources happening, right, then you have a photon budget crisis because you will have a tension. So all the photons coming out in the early universe, they start to ionize the medium and they do the scattering of the electrons. And if you try to compare results of the ionizing emissivity with the CMB, then you realize because you have so much photons and you have these massive galaxies, then you will ionize much earlier. So you will ionize by redshift of 10, whereas we know ionization should happen around redshift of 6 or so. So that's another interesting tension with CMB. Another painful paper that is very painful to me when they say no tension, because the basic idea, what they say with this, they have a simulation and they say, well, our physics is nice and complete, and it's a resolution problem. If you are able to resolve very dense gas in the early universe, and you go down to resolution of 10 to the 4 solar masses, very, very tiny resolution that is very hard to capture, then you're naturally reproducing everything, because when you have you capture this dense gas, then you have too efficient star formation. So most of the models fail because they don't have the ability to go to high resolution. So that's also lead to the question whether most of the galaxy formation models we have in the market, they are not resolution invariant. So once you push your simulation to higher resolution, sometimes you need to tune your parameters and tweak that. So that's a very, and I don't think we will ever know the correct physics without solving this problem. If we don't have an invariant, like simulation that is invariant and convert with respect to resolution, it's very hard to know what is the issue, okay? Because you run high resolution, you get too efficient star formation, you run low resolution, you get low resolution. So it's a very, or maybe that's belong to the models they use. So it's a very interesting debate. The last one is to highlight the fire simulations, and they argue that, well, because our models also reproduce this observation very nicely because we can capture burstiness in star formation. So if you look at the history of all galaxies they have in their model, they have bursty star formation, and therefore, like with the bursty, like you have an explosion of supernovae, and you capture all these tiny processes in subscales, then you can see the peak for star formation going up and down, and then maybe you can solve the problem. And they show that they could actually fit to the observation of JWST very well if you have really bursty star formation, which you can expect in high redshift when you have dense gas and you have maybe weak feedback and so on. So I wanted to stop here, and after highlighting this and ask the question, who believes there is a tension or not? And then I will try to ask the question at the end again. Do you believe there is tension? You don't believe there is tension? No?
There's tension.
There is tension, right? No? Anyone says no? No tension? Okay, let's see. So I'm gonna also contribute to this discussion by showing you what I can do, and then we can talk at the end whether there is a tension or not. So it's naturally to think if we require too efficient star formation, maybe the problem is how we model stars and how we model star formation actually in our simulations, right? So what is the motivation for the work that I'm going to present is that most of the traditional star formation models are tuned to reproduce observations. So they are not predictive. One of the famous models that has been successful for almost 20 years now, over 20 years, is the Sprengel and Henquist model. It's a hybrid multi-phase model. Then you assume that each star forming gas has like cold clouds within warm medium. And then of course the star formation is simply just it's related to the cold density of the gas divided by the time scale for star formation, right? So what they realized, this is the earliest attempt. This is the famous Schmidt law, surface density of star formation, surface density of gas, and this is the dashed line is the observation, right? And the dotted line is one of the earliest simulations they did run. And they realized if they tune this guy, the time scale for star formation in 1 gigayears, they can match this, right? And by magic, once they match this relation at low redshift, they can reproduce major quantities in high redshift. That's okay, but it's very hard now to link this to the physics, because if you match to the observation, you can't actually, if you tune to the observation, you can't make interpretation of the observation. But if I try to develop a model that is from first principles without tuning to the observation, then I can tell okay, maybe I get closer, maybe I need to add feedback, maybe I need to, so then you can gradually play with the physics to know what is more important to match something like this. So then these other problems we have is that most of these simulations we have in the market, they don't have like the varying ISM conditions. They probably also depend on the resolution, and this is a very problematic. I think we, like theoretical community, really need to push the limit towards developing resolution invariant simulations. And then they don't have this multi-phase ISM where we have great progress in the ISM simulations where you can capture different temperature range, warm, cold, and very hot, and so on. And all these are missing from the simulation. So what the direction can we do? So the question I'm trying to answer here is that can we use ISM simulations, right, to inform star formation on large scales? I don't know where is this, okay. So one of the nice simulations in the market, there are many, but one of them is Tigris, which has had 3 phases, modeling of the ISM with feedback, supernovae, and many interesting physics. And the basic idea is that, okay, so let's look at this Milky Way, right? You can take a slab of the galaxy disk, right? The same slab here. And then you can assume that you could model the gas regardless of the environment around it. And then you try, because you do this, because of this assumption, you would be able to capture very tiny details of the gas and hydrodynamics. So the assumption here is that, okay, any simulation we could run, it could be representative at the level of 1 kiloparsec scale as a batch in the from a telescope galaxy. And then you can model the gas vertically. You go to scales where like up to 5 to 10 kiloparsec in gas. So all these simulations, basically like vertical simulations of gas, hydrodynamic and magnetic field, magnetohydrodynamic, and you capture all the sophisticated physics, the cosmic rays, supernovae, all the feedback and all the different components that influence the star formation. And this is just the differences between the different chunk of gas as you go to different places in the galaxy, right? Now, with this resolution, as the level of 1 kilo/sec is resolution, there is no way we can run hydrodynamic simulation for galaxies using this extreme resolution. So the question is that, can we use insights from these simulations in order to inform modern star formation on cosmological simulations? This is one of the snapshots of some of the simulations that is run with the Tigris framework. And with this, you see here, you have 1 kilo/sec scale. You have 4 kilo/sec up and below the mid plane, if we can say. And you see the evolution of the gas in this scale you can never capture in these large scale simulations. So how do we use this actually to inform this, to inform forming stars on large scale? And this is this is going to be probably my only equation slide in this talk. And this led to the development of the PRFM model, which is the pressure-regulated feedback-modulated model by Igor Stryker and Kim Chang-woo from Princeton. And it is built on some classic ideas. It's not really a new ideas. It's ideas that, like the ISM conditions and the star formation, they co-regulate each other to arrive to equilibrium. Right? And everything is affected star formation, affected by the conditions of the ISM conditions affected by the star formation. And the model assumes equilibrium in systems. So in equilibrium, if you have a vertical equilibrium within your galaxy, the pressure is similar to the weight. That's a statement you can say for any vertical equilibrium. And if the pressure, you could write the pressure as sigma effective squared, which is the velocity of the gas. And this is just the density of the gas, the volumetric density of the gas, which you can write as surface density of gas divided by the scale height. The scale height for the gas is one of the tricky quantities you can resolve in simulations. It's very hard to resolve. It's very hard to resolve the actual lengths of the gas. And because you don't resolve the scale height of the gas, you could underestimate the star formation by a lot. So you really need to capture these scale, like resolve the gas height of disking galaxies. And then that will lead you to different, you can have different contribution to the pressure from the thermal pressure, turbulent pressure, and magnetic field. Then you go to the weight component, right? And then in that weight component, you can integrate the density, right, over the gravity acceleration. So then you have different components in the gravity, right? One related to the gas and stars and dark matter. This model allows to account for the contribution of dark matter to star formation. Most of the models neglect that. It's a small contribution, but if we talk about precision in cosmology and improving physics, we should account for every single source. So that gives you the weight in dark matter. And then if you solve these equations, you can come up with equations for what is the contribution of gas to the weight and stars to the weight and the dark matter to the weight. And then with solving this equation, you can come up with prescription of assuming vertical equilibrium, what would be the gas height, the gas scale height. And that's something you can use in your simulation. Anything here is still pen and paper. There is no any ISM simulation yet, but we will motivate that in a second. Then for the star formation, this model assumes that the star formation is not really related to the density. It's rather related to the pressure. So the more pressure you have, the more star formation you can predict. And that's the difference in this model. And it's formulated in a way that the surface density of star formation is related to the pressure and normalized by epsilon, which quantifies the feedback in simulation. Okay, so that's nice. So this is very nice. Everything you can link it in a simulation, you can develop this, you can write it. It gets tricky, of course, if you want to compute these quantities, you have to compute them locally. I will talk about this in a second, but everything is clean and nice, right? So where the ISM simulation coming from these two things. The things that we cannot capture and model in simulation is sigma effective, the gas velocity. Very hard to model this. It depends on the turbulence. It depends on many factors. We have some values, nominal values from the local universe, about 10 kilometers per second, whatever, but we don't know how this quantity changes as a function of pressure or metallicity or whatever. So that's something we don't know. The other thing is that the feedback, and because that's tied to the capturing the small scale processes, we don't know how to model this feedback yield in the simulation. And this is where the ISM simulation comes in. It's very basic. So for the gas velocity, what we can do is that we can go to the Tigris simulations. These are the different 6 simulations that I showed you, just these while back. because they brought different density range and different initial conditions, but the same model. So we can stack them in the effective equation, which is the pressure as a function of density. And then we see, oh, well, there is a very nice correlation between these things, right? Like they have a very nice line correlation between the pressure and the density. And then we can fit a line to this, and then that's the fit to digress simulations. And then we know that the pressure is related to the sigma square effective this equation, how to model the pressure. And then if you solve this equation with that equation, you can come up with some relation that the velocity of the gas is proportional also to the total pressure. So now you have a star formation proportional to the pressure, and you have the sigma. So now this is a subgrid model that is coming from the ISM simulation, basically. Just fit to the ISM simulation, playing with the theory, and then you can come up with the relation that how the sigma gas is related to the pressure. Then we are not done yet, and that model is new, right? Like we don't know how to model this in simulation. So now for any simulation could use this relation following this ISM simulation, if you are able to calculate the pressure, of course, which should be doable because we have all the information. The second thing is the yield feedback parameter, right? And as you see here, this is the epsilon as a function of pressure again. And as you see, the feedback is wild, right? So you have a huge range, the scatter is high, and it's a data science problem. You can look at it and say, can I fit this, can I not? And then if you look at the median and the mean relation of these different simulations, 6 simulations I showed you, they passing through somehow the mean relation, at least it's correlated negatively with the pressure. So let's do a fit for that, and that gives you the epsilon as a function of pressure again. So you can use this relation now to find out. So as soon as you have the pressure, you can get the sigma effective from the sigma effective. So that's the flow, right? You have the pressure. You can get what is this? So once you have the pressure, you can get the sigma effective. Once you have the sigma effective, you can find what is the gas height for the gas. And once you know that, you can actually also compute what is the epsilon here, and then you can calculate the star formation. So it's a loop together, and it's a very easy loop. It's the only thing that missing is that you need to know how to calculate the pressure, and then you can use these recipes to do this. Of course, these recipes does not account for the scatter in the simulation. That's a step we need to think about, how to model the scatter in this relation. But at least at the level of the mean, we are able to calculate that, okay? So how do we do this analysis? So this is a slab. So we decided to use TNG 50 because this is the highest resolution cosmological simulation we have. And what we do, basically, we have the sample selection and analysis. So we go to the simulations from redshift of 0 to 2 or 6, it doesn't matter. What we do, we take one galaxy. So this is like a slab of the snapshots of the universe within 6 megaparsec scale. You take one galaxy, you move to the galaxy. This is how we calculate the quantities. This is the painful part in implementing this model because it requires you to focus at the level of the 1 kiloparsec scales. So you take one galaxy, you grab it, you calculate what is the angular momentum direction, you rotate to face on your galaxy because you need the midplane for each galaxy, and then you grid that into 1 kiloparsec scale. You put a mesh of 1 kiloparsec scales, and then you try to project the quantities, right? So then now you can calculate what the star formation is, which is this is the surface density of star formation as coming from TNG. So that's not our model. Then you can calculate what the stellar density, what is the gas surface density, and in the same way you can calculate all these positions here because these are the quantities you need. You need to calculate this. You need sigma gas, you need sigma star, you need these things, and these things are the things that we can easily compute after this, right? So this is all done in post-processing. We just go into galaxies where they have masses from 10 to the 7, 10 to the 11, so we don't go to very unresolved systems. We require, like any galaxy that you see here in this talk, it has a minimum of 100 particles for all types, dark matter, stars, and gas, so it's very resolved, and it doesn't go to the very low regime of star formation, so maybe we can expect some diffused and numeric effects. So that gives us a very controlled sample. And let me show you the results we get. So that's a big giant plot. Let me try to unpack this. People, especially the observers, they like to think of star formation as the depletion time, which is the consumption time of the gas, right? Like, which is basically an inverse relation with the star formation. Too efficient star formation means you have a short depletion times. So this is the depletion time, and this is the dynamical time. What you see on the left-hand side, this is our prediction from our model when we process it with the fitting function we have. This is the Sprinkle and Henquist model, which is basically the output of TNG. And this is here, like the data you see here, this is all galaxies in the simulation at redshift of 0 and 1. So we take like the studies in the ISM, we don't care about the masses distribution. We take each 1 kiloparsec batch. We flatten all of them as one array, big array, and then we do the histogram. We want to see how the ISM physics evolved as at the level of 1 kiloparsec scale. And then as a reference line, we know from traditionally that there is maybe a relation between the depletion time and the dynamical time. So for a reference line, we plot this line, like whether it's 1%, 10%, 50%, or 100, whatever, 100% of that. And then we compare, right? So, okay, so let's look at the Springer and Henquist model. So also this is color coded by the total fraction of star formation. So anything is light, that's the outskirts of galaxies. Anything is dark, that's the center of galaxies, okay? And then let's look at here, right? So Springer and Henquist really following this constant relation, right? So that's the depletion time is really correlated to the dynamical time by 1% or 10% or whatever. And it's because the Springer and Henquist initially was tuned to this relation. So it's no surprise, actually, it matches this relation very well. But the prediction from our model is that as you go to shorter dynamical time, you have even shorter depletion time, which suggests that our model predicts non-constant depletion time and dynamical time relation. And that's very interesting, right? Like, it's not as people thought before that there is a constant relation. Okay, it's only 10% of the dynamical time you can deplete the gas and form stars. So that's one of the results we have. The other one is the global Schmidt law. And it's the same thing, right? So light colors, these are the outskirts of galaxies, dark is the center, top is 0, redshift of 0, bottom is redshift of 2. This is the Schmidt law, right? The surface density of star formation as a function of surface density of gas, right? And the stars here are the 6 simulation of the ISM simulation that I showed you earlier, right, from Tigris. So we can overplot them to see how things look like. And this is a very interesting plot, right? So, okay, so in the right-hand side, you have the Springer and Henquist model. Left-hand side, we have the PRFM model, right? And they are different, okay? And then you have the dashed line is the observation when you assume in this relation molecular correction. So then you can get this different slope when you assume a fixed alpha CO, right, for the molecular gas, and then you get a very different result, but it's not, the slope is not that very different. And of course, Springer and Henquist again, because it has been tuned to this relation, it reproduces this very well, okay? But in our case, what we see, right? So let's try to impact this, right? Because that's very interesting, right? So the first thing is that what you see where we have data from ISM simulation, right? So we have data here and here, but we don't have data here, right? So the first results we can say clearly is that both models are consistent with observation, right? So if you see, this is the observation, this is the dashed and the solid line in our model, and here, like, well, we are really consistent without tuning to the observation, which is, this makes it very interesting because we have a predictive model now that has never been tuned to this observation, but is able to match the observation without tuning, which is a plus, because now we can make interpretation and see what is more important and what is not. Like, this is related to the pressure, star formation related to pressure, the star formation related to density. So it's a different kind of model, but in the regime where we have data from Tigris simulation, okay? What is the second result we have here? Let's go here. And the second result is that as we go to higher densities, and now you probably can guess how we can solve the problem with JWST. As you go to higher densities, everything is extrapolation of the model, right? Because we don't have, currently we don't have ISM simulation that broke this density range. So anything I would say would be pure extrapolation. But the model actually, as you go to higher densities, you're predicting too efficient star formation at high densities. And of course, high densities is basically the mimicking the the high redshift universe, right? Because we expect the redshift is very, very high. So when we saw this, we decided, okay, let's go back to the problem, the challenge we have with the JWST, and this is what you see, right? So this is basically you have the luminosity function at redshift of 9 and 11 and 12. Okay, this is the luminosity functions, of course, right? And these all the different data from JWST. What you see in solid, right, is the Springer and Henquist model. Okay, what you see in dashed, this is basically one prediction of the model PRFM, where our relation for the sigma effective and the epsilon, the feedback, they only depend on the pressure. We have a new model now for PRFM simulations where actually they account for non cooling radiation like non-homogeneous and homogeneous radiation. And then you can actually run the model for different methodicities. So we have a different fit for the sigma effective and the epsilon as a function of pressure and metallicity, and they give us different relations. So now we need to find out which one is the correct one, which is that's a work in progress. But as you see that the Springer and Henquist model, the solid line that uses the star formation is related to the density is very low as compared to all the measurement from redshift of 9 to redshift of 12. But we are, without tuning to the observation, at redshift of 9, the classic model gets very close to the observation, which is really nice. As you go to much higher redshift, the model where we account for variation in metallicities gets much better with the observation. So now we need to find out, and we're implementing this in the fly now to try to find out which results might be better and how they interact with the feedback, basically. So this is how we solve the puzzle, is that still the problem of the resolution exists. It doesn't really change much. But what we find here is that you have you can reproduce this observation by having a star formation prescription that is depending on the pressure, not depending on the metallicity. Like don't depend on the density. It's better to model things from the pressure, and then you can have this fitting relation to ISM simulation. And you could use any ISM simulation. It doesn't have to be that, right? I mean, you can have the same prescription, right? In the same prescription, the only thing you need is how you model epsilon and how you model sigma effective. And if you are able to find any simulations that is able to give you a relation between sigma gas and pressure or anything, whatever you want to model with, these are the missing pieces that we don't know how to model in cosmological simulations. And if we are able to find any way, in this case, we use Tigris simulations. But I think this is like I think probably it's the first attempt to try to move away from tuning models to observation. And it seems to me what we are happy about is that we are successful in regard where we have ISM simulations. We are able to match to the observation without tuning, which is actually extremely really nice. And we have this extra predictions that the star formation is too efficient at high densities. And with that, we can actually nicely recover what JWST requires us, which is the too efficient star formation at high redshift. So I think this is the key results we have. That's the PRFM predicts this short depletion times, leading to a more star formation at higher redshift densities. Both models are consistent with the observed Schmidt relation in this range of 1 to 100 solar masses. And the PRFM does so without observing the observation. I think that's the biggest win we have. And then we think that we could actually naturally explain the high Z UV velocity function and our on-the-fly implementation in the progress. So yeah, so I think with that, my official talk is done, but I can talk about something else if there is time. So thank you very much. I mean, we can have some questions if, and then we can move to something else. Something should be cool to know.
Are there any questions?
Yeah.
So, thank you so much for showing this great model. I actually have two questions. One is, do we have an intuitive understanding of why PRFM predicts higher star formation rates at higher densities as opposed to the Springer-Lundquist model?
Yeah, I think this is mainly coming from many places. So the first thing is that it comes from this relation. When you have when the feedback, right? When the feedback is have this inverse relation with the pressure, that impact your prediction for star formation. That's one thing. The other thing is this is one thing that is definitely impacting this. The other thing is where is the relation between the dynamical time and the depletion time. So if you use a constant relation, you might not expect to see that. So this, because I mean, the dynamic time for things in the early universe are actually smaller, right, than the dynamic range at the local universe, and therefore you have a shorter dynamical time that would correspond to shorter depletion time, and then you have to efficient star formation. So this is the things that I think it's a combination of two: the feedback and the relation between depletion time and dynamical time.
There's a question online.
Yeah.
Kevin, if you want to unmute.
Yeah, hi. Thanks for the interesting talk. I'm sorry, just. So one of the things about this is that you showed a couple of observational underpinnings. You know, from the start, you showed some pretty early ones, but then in your last couple slides, you showed a little bit more mature luminosity functions. But I'm pretty worried about the state of the luminosity functions. At redshift 9, I think we're okay. But redshift 11, 12, 13, and above, it starts getting a little more dicey in that we don't have a lot of spectroscopically confirmed, and it is very easy for us to be tricked with photometric redshifts alone. Our photosees are pretty good, but in many fields, the lack of filter selection, filters, you know, and depth really hinders us. And so, like, I get pretty worried about how well we know the luminosity function in some of these fields, you know, some of these smaller fields, or, you know, like maybe lensing fields and stuff where, you know, we can go down pretty deep, but you have to do some pretty careful corrections. And that's something that I worry about, because, you know, Michael Boylan-Kulchin's paper was responding to a set of papers that were like, look at these high mass objects, not highly luminous objects. And those masses were entirely incorrectly predicted in the original papers. And so, like, I just worry about how much are we going to need to actually change our theoretical models to match, you know, once we have more robust luminosity functions in the next 2 or 3 years. I'd love to hear what your thoughts are on that.
Yeah, no, thank you for the question. That's interesting. I mean, that's related to what I said in the beginning about systematics in the observation, because there are some people say, oh, you know what, my theory is beautiful. And it depends on, there are different theoretical studies take different approaches, right? So you could say, well, I mean, I don't believe the observation, and let me wait, and then you just use your model. And there are many papers doing this. There is already over 100 papers. Many of them, they do this. There are the other approach where you say, you know what, let's look for a new physics and let's look for a different way to do this. So even in my talk here, the motivation to implement the PRFM it's not because we wanted to match with JWST, it's initially actually because we wanted to have models that are more predictive. And we just get this for free, that we have this too efficient star formation, so we can sing about it. But it's not, that's the motivation. That's the first thing. The second thing is that for this luminosity function, I agree. I mean, we have very poor constraints on the the front end of luminosity functions. We can't really talk a lot about it. We have a couple of spectroscopic confirmation, right? Like with gates and NG deep, right? So we have some of the, in some magnitude range, we can, hopefully these are spectroscopic and maybe they are okay. But I agree, I mean, most of them, they are really coming from photometric. And if you see my first, this, I didn't mention this, but in this nice summary, we were all happy about this object that came out in the early release about redshift of 16, and then people found later that the photometric redshift is wrong, and it moved down to redshift of 5, right? So that could happen too. But it's a question is that whether, like, which philosophy we wanted to do, and I think it's perfectly fine. You can blame your systematics and you say my view is beautiful. So far we don't know, but there are many hints. It's not only actually. It's interesting why, because I mentioned this briefly. The 21 centimeter global signal, when it was discovered by Edge's experiment, they found the same debate, and they found also the trough for the signal is too deep, and therefore you require also too efficient star formation. So the too efficient star formation also you need for 21 centimeter and radio side. If you look at the black hole masses in comparison with the observation, also the black hole masses are a lot bigger than what we expect. So in most of the observation, in different observations, we still actually see the need for large objects and bright objects, whether galaxies or whether AGN, right? And that's also give you the question is that, okay, so if we have these bright AGN, why they don't actually quench star formation and why the star formation is so high? So there are many questions we don't know the answer for, but the push from different experiments and different community. I wrote a paper about the 20 centimeter similarity in debate and JWST. And in that letter, what I tried to make the point is that it's two different communities. They don't talk to each other, but they found the same debate at a high redshift, and both of them, they require two efficient star formation. And I think that's, if you see most of the models and most of different observations, they are going into the direction of two efficient star formation and too bright galaxies and too much of black hole mass, then maybe they're right, maybe not. We don't know. But yeah, I mean, it's a very degenerate problem, right?
Yeah, I think that
Yeah.
it is a boost. There is a boost. Lily Whitler on the Jade's team is about to come out with a paper that shows, I think, pretty robustly that at most MUVs there's a shift from what would be predicted, but I don't think it's as extreme as was seen in the early data. And I think we have to be very careful about, over modeling and making the problem worse in the other direction.
I agree.
Hassan?
So I have a question. You showed kind of your calibrating relationship for the feedback, and that there was like a huge amount of scatter in it that you said was kind of a data science problem. And I'm wondering how that uncertainty then maps to your luminosity function in terms of kind of what you predict.
Yeah, that's true. I mean, as I said, I mean, the model is not complete because the problem is that with the feedback, it's affected by recent explosion of supernovae, so everything gets bursty and then come back, and it's very hard to capture a smooth relation. That's one. But if you look where the median distribution as a function of pressure, these are the points here, which shows you where is the median value, where most of the data is there. So the scatter is, I don't like this plot because it doesn't show, I mean, it's all points, so you can't really see where is the center and where is the, yeah. But I think this is just like quantifies this with these error bars, so we are following the median relation. So it's correct. Regardless of the environment in that 1 kiloparsec patch of the universe, we will always, for 10 to the 4 pressure, we will always apply 10 to the 3 feedback. So that will always be there. So there is no variation. It's 1-to-1 relation so far. Ideally, one could model this, I don't know, machine learning, or you can have assume the scatter is Gaussian and then you sample from there and see the effect. But that's also going to be extra assumption to make unless you model the actual density here, right? But I agree. I mean, that might impact, but we don't know. I mean, but it will not change the trend, right? As you go to higher pressure, you will always have lower feedback. So maybe not too much, but maybe yes. I don't know.
I have a couple of questions, and the first one was more sort of a comment on that UV luminosity function plot that you just had up, the one from Harakane 2022. So I think it's way at the beginning.
Okay. Yeah.
Yeah, thanks, that one. So I think it's true that there's more UV bright galaxies than people were expecting before JWST started. But like specifically in this plot, if you compare the point on the right to the point on the left, there's the same number of really, really bright galaxies at redshift of 13 and redshift of 10. And that seems like that is probably wrong. That's probably a result of overestimating the number of redshift 13 galaxies, because for it not to evolve at all would be very strange, even though there's not that much cosmic.
I mean, also, I mean, one of these points could be actually estimated with on galaxy too. So we don't have enough sample too, right?
Right.
So that's a problem too.
Yeah. So the other question, which was more like model specific, was about the star formation recipe. The prediction of the Schmidt relation, or the comparison to the Schmidt relation, and you mentioned that the Springle and Hörnquist model is basically tuned to fit the Schmidt relation that PRFM is not. But what I'm wondering is if somewhere in the assumptions of the PRFM relation, there's a normalization that is in there, because I'm guessing that you aren't predicting the, efficiency of star formation completely from first principles. Or do you feel that you are, that you're?
I think that the only problem in this analysis that I know of, I can say it, and thank you for that. The only problem here is that it's one complaint I can say fully. Where I'm going is the plot for let me see, where is this? Why is it different? Let me see. Where is that? Where is this? Yeah, here, right? So the problem we have here is that we have we are testing this now and we are okay, I think. But the challenge with this analysis is that it's not one-to-one comparison. Why? Well, it's not one-to-one comparison because all the analysis I'm showing here is done in post-processing, right? So the gas and the physics within TNG has been evolved already with the Springle and Henquist model. And the assumption we're making is that, okay, this is the gas condition. Let's apply our recipe and see what we get, okay? So ideally, we want to compare this when we implement it in the fly and then run the model and let the model interact with the feedback and interact with many things and evolve the gas independently of the Springle and Henquist. Then we can test and then we can see the true result. Right, and we have made tests now, initial test, and we are going into the same right direction that there is too efficient star formation. Things might change in amplitude a little bit, but we still, the qualitative results is the same that we have that so far. But that's the only problem we have in this analysis, that the gas has been evolved with one model, and then we are applying another model on top of another model to see to compare the two. So that's not consistent. But that was very important analysis to take in order to have a baseline to see what things we can expect.
More questions? I have one that is along the same lines, maybe, but we have 10 more minutes. If you want to pitch something else, I can bother you at dinner with my questions. So
yeah, so I can show you something fun I have been doing, which is basically machine learning oriented. But let me see if I can show that. So recently I have been doing, so this is a QR code if you want to go in and see. So recently I have been really interested in, I joined Kaggle at Google for a fellowship. And then we have been thinking a lot about how actually to use large language models to enhance research productivity in the field, right? And we know that ChatGPT, we can't really convince you, is not everybody using that. And the field is moving towards this, but slowly. We don't have, maybe in the field I'm aware of maybe 3 groups are actually focused on developing LLMs for Astro. And it's very interesting actually. Discussion. So anyway, so that's one of the presentation, but I think one of the challenges we have here that's coming from this. So this is the number of cumulative submissions as a function of here from archive, right? So, and AstroPH is the red one, right? So by 2021, we're already hitting like 800,000 papers, right? So if you're starting a new project, it gets very hard for you to know whether your project even have been done or not, whether what are the relevant problems, and what are the relevant literature you do. So I think we need to automate this. We need to have these tools that can help us to do so. And we know that in large language models, you usually fine tune them to develop like domain specific models. It usually works much better. So what the pipeline, so I developed something called Cosmological, is online, you can look it up and see it. So, and it's a chatbot, right? So how do we do this? We have 3 components. You have the dataset generation, fine-tuning and deployment. So for the dataset generation, I selected only, I focused, okay, that's a starter, let me be small. And then I started small. So then I selected abstracts from this astroph.co, only cosmology papers, within 2018 to 2022. That gives me about 3.5K abstracts. That will be used for fine-tuning, and for testing, I go to papers that came in later, just for the fun of it, to see whether, make it challenging and see whether I can get that. So I take for testing papers that came out 2023. And then you can use a combination of something called LangChain, which is mainly for having a very good prompts for these models and following the history and stuff. There is a model called Llama. It's a framework where you can just run large language models locally in your machine. And then I used Llama 3.1, which is the meta model to generate the data set. So in order to have a chatbot, you need a Q&A data set. We don't have that in the field. So what you can do is that you can pass the abstract to one of these large language models and you tell it, okay, given this context, given this abstracts, can you generate a Q&A answer, right? So you have to play with the prompt. So then the Q&A answers is not specific. It doesn't tell you like, according to this context, do this, or according to this text, you want it to be a bit general. So you write a prompt to do so. Then once you have that, you generate all the 3.5K for fine tuning and the 1000 for testing. Then you can go and because it's a Google fellowship, I have to use Gamma, their models. And then we use that to fine tune with these questions. So the model has been already fine tuned, like trained in the beginning, but then you start fine tuning to make it domain specific. And then we made that, and then during fine tuning, we have about 95% of accuracy. And when we tested on samples that came in from articles later, we have about 75% accuracy, which I think it's very, very, very nice. And then you can move the model to Hugging Face, which is one of the biggest now open source models, any machine learning model that you can use there. And they have a nice interface for deployment of any model you can do. I can show you some of the things that it can do. This is very small. I can try to make it big. But the model is able actually to answer multiple choice questions, even though I didn't train the model to do so. So this is one of the benchmark data set that's coming from AstroML Lab, which is a group between, I think, Argonne National Lab and University of Illinois and Ohio State University. They do some fine tuning for models, and they have this benchmark data set that they have developed with some people from ADS, I think. And then the right answer is here. What is the primary goal for calibrating subgrid photo in cosmological simulation? The right answer is D. And I was getting the D. I was very happy about that. The other thing that also I tried to test, which is, I'm very interested in the question of brainstorm idea for project, especially for students, especially for if you fine tune in recent papers, try to find out like what are the timely things to do. And then I was able to ask the question, okay, please list 3 ideas for interesting projects to work on in cosmology, to advance cosmology. And it came about like, okay, measuring omega matter and lambda, whatever, from cosmic chronometers, tracking the expansion history of the universe, and making the Hubble tension. We have a tension in Hubble, so let's make precise measurements for the Hubble, right? And yeah, so I think all the projects I'm a big fan of open source. So the model card in Kaggle, you can take it, and if you want to run it yourself. In Hugging Face, there is the card model, there is the app for Gradio, and there is also the GitHub release for all the code. So if you go to GitHub, you can find all the codes, all the data, the Q&A answers, all the steps, all the details, everything is there. I probably have maybe 1 minute to show you the actual application for it, right? So this is the app. You can go to it if you go to that QR code, right? And then you see, like, let's collect one of the examples here we have. So what is the primary reason for the decline in number density of luminous quasars at redshift? And that's, they say, quenching. You can ask a question, what type of coupling in inflationary models can affect prediction of illuminating and non-minimal coupling to gravity, and so on. So you can come up with different questions, and hopefully that can be useful. This is a very small model. It's 2 billion parameter model. I'm training more of the models and see whether, but yeah, so I wanted just to share that, and maybe something, if you're interested, let's do something. Thank you.
We tried to do these, but for a much smaller scope than what you managed to do, which was just have a chatbot that can read the documentation of a code for you. That seems like a much smaller scope. I was using a 7 billion parameter model and it failed miserably. I couldn't get it to work in any sense that was useful.
Okay.
So what's the magic trick here?
I mean, did you fine tune or were you using RAG?
I was trying to reuse RAG.
Yeah, RAG is different, right? So RAG, if you have a very good embedding model, And if you have a very good model to use, then you should have a good results. And it might also be from the way you're reading the data set. Also, the vector store might not be very self-contained and problems. So sometimes these vector stores, they fail to read tables very well and to connect them between different things. So I think if you play with the vector score reading and the embedding and the model, maybe hopefully it should.
So you would suggest to push with RAG rather than
I mean, RAG is a good start. You can still fine tune, right? You can still fine tune and find that if you especially want to use a larger model to have a different thing that. But yeah, but that's a very, we are trying to do this the same with camels too.
I guess, were you trying to train it on the documentation of one code?
I wanted
That might not be a large enough set to,
might say it was
I
a
don't know how
lot.
much documentation.
No, it's a well-documented code. My idea was
Right,
to have
but-
something for the student to ask the first question to the
Sure.
model first. And then when the model hallucinates, then I can jump in and correct it. But I am nowhere near to realizing that. Okay. Is there any other pressing question? Check on.
The field is moving towards this. We need to use this, otherwise. I mean, it's very interesting in Google. Some people, they actually developed like code, like one of these chatbot to mark exams. So they would the exams or whatever, it makes the interpretation, whatever. It's been very interesting actually to see the different application.
I just wanted to mention that it got the decline in the number density of luminous quasars thing. It got the answer wrong in an interesting way, which is that it got the sense of time wrong. Because it gave you the answer for the, you know, the decline with time going forward rather than time. But that's something that screws everybody up is like, you know, is time going forward? Are you using increase or decrease in the sense of like increase with redshift means backwards in time?
Yeah. I mean, it loses information.